Now, the processes that we've been considering so far are irreversible. This means that we can't reverse them through a series of small changes. So once we've dropped our egg, it's not physically possible to put that egg back together. If I play the video in reverse, you know it's in reverse. Now, so far we haven't learned about any physical laws that prevent that egg being put back together. It doesn't break any of our conservation laws, such as conservation of energy or conservation of momentum. So in order to explain why that egg can't just go back together, we need to introduce a new property. So the property that we're going to be considering now is known as entropy, and it has the symbol S. Usually we're going to actually be considering change in entropy, which has the symbol delta S. Now, the entropy postulate tells us that if an irreversible process occurs in a closed system, the entropy S of the system always increases, it never decreases. Now, this entropy postulate is often known as the arrow of time because it tells us the direction in which irreversible processes have to occur. Now, there's two equivalent ways that we can define entropy. We'll be looking at one of them in more detail in this lesson, and then we'll be leaving the other till the end of the entropy topic. So the first way is in terms of the system's temperature, which remember has the symbol capital T, and the energy it loses or gains as heat, which has symbol Q. So we'll be coming back to look at this one in more detail. The second way that we can define entropy is by counting up the number of ways that molecules can be arranged. So this one's really interesting, but we'll come back and look at it at the end. Okay, now entropy is a function of the state. So we've already seen quite a number of functions of state. We've seen that the internal energy is a function of the state. The pressure, volume, and temperature are also all functions of the state. The work done and the heat were functions of the path, not of the state. So if we want to calculate the change in entropy to get from some initial state to some final state, then the change in entropy is given by the final entropy minus the initial entropy, and by definition this is actually equal to the integral from the initial state to the final state of dq on t. Now, as an example, let's go back and consider that really boring example, isothermal free expansion. Okay, so it's really boring, but at least it's fairly straightforward. So you've probably forgotten because it was so boring, but isothermal free expansion is when we have all the molecules compressed into half the volume. So before we had them in the bottom half of a cylinder, we can also put them on one side of a little valve. And then what we do is, without doing any work, we open that valve or gently break that membrane and allow the molecules to expand out so that they fill up the whole volume. Now, we can represent this initial and this final state on a PV plot. So if we do that, it looks a lot like this, where with the initial state, we've got half the volume, but double the pressure of the final state, and then the final state has double the volume of the initial state, but only half the pressure. Now, technically, we can't draw a line on the PV plot to show this isothermal free expansion because the gas isn't at equilibrium, and the paths on PV plots represent a series of equilibrium states. But this is where it gets kind of exciting, and you've seen this trick a little bit before. What we can do is, because entropy is a function of the state, it doesn't matter how we get between that initial and final state if we want to calculate the change in entropy. So we can choose the nice easy example of an isothermal expansion from that initial state to that final state. And since entropy is the function of state, the change in entropy should be exactly the same. So you may remember when we were looking at specific heats, we used this trick for the change in internal energies. We're just doing the same thing now. So if we wanted to consider what this would look like physically we could achieve this if we had the gas compressed with some masses on it over a warm water bath to keep it at the constant temperature. And then if we slowly take the masses off the top to decrease the weight force down, the pressure is going to decrease, and so the volume can expand. And if we do that nice and slowly, then we'll remain in equilibrium. So then we get a nice line on our PV plot that looks like this. And now we can fairly easily do the calculation of the change in entropy. Because this is isothermal, the temperature's not changing. So when we do the change in entropy is equal to the integral from the initial to the final state dq on t, t's constant, so we pull it out the front. So we've got the change in entropy is equal to 1 over t times the integral of dq, and the integral of dq is just the amount of heat that we've added. And so we can just say that's q. So for our isothermal free expansion, our change in entropy is just equal to q divided by t. And in this case, we're adding heat, and the temperature is always positive because we can't have negative temperatures. So in this case, the change in entropy has been positive. Now, this actually works for anything where we've just got a small temperature change. As long as the temperature change is small, then we can approximate it as an isothermal expansion. And so when the temperature is almost constant, we've got that the change in entropy is equal to Q divided by the average temperature. So in a second, you're just going to practice using that one a little bit, that formula, which holds for small temperature changes. But notice the trick that we've used here, because with this isothermal free expansion, that was an irreversible process. We couldn't randomly get all those molecules to compress back down into the bottom half of that cylinder or onto one side. That's just statistically not going to happen. So this is an irreversible process. So what we did was we replaced our irreversible process with a series of reversible processes between the same initial and final states, and that allowed us to calculate the change in entropy. So that's a trick that you're going to see used a few times in this lesson.